All right, so in this video, we're going to kind of talk about the water and its interactions as an acid and or base. And so when we consider Bronson-Lowry's definition of acid and base, right, water could be either or, just depending on what it's reacting with, right? And so, like, for example, if you were to consider NH3 plus H2O, right? What we have, and NH3 is actually a strong base. What we have is NH4 plus OH minus. All right, and so NH3 being a base, all right, water is going to act like an acid. Okay, and then what you're going to have the conjugate acid with the conjugate base. Okay, now on the flip side, if you have something like HCl plus H2O yields Cl minus plus H3O plus, well, we see that HCl is an acid. So because it's an acid, water is going to act like a base. All right, and thus you're going to have, in this case, the conjugate base and the conjugate acid. All right. And so, depending on the substance, all right, water is going to act like either an acid or base. All right. In this case, we say water is amphoteric. All right, which simply means it's just a substance that could either act like an acid or base, all depending on what's reacting to it. All right, and there's other amphoteric substances. So some examples, some other amphoteric substances is like HCO3 negative, H2PO4 negative, HPO4 2 negative, HSO4 negative. These are all also amphoteric substances. So water is not the only one. All right, it's water is special, but not that special. All right, but let's just say we don't have any other substance. All right, water can still react in such a way, in this way, even though you don't have any other acid or base present. All right, so this is what we call the auto-ionization of water. All right, and so it's basically water ionizing itself. All right, and so the reaction is basically H2O liquid plus H2O liquid. And what's going to happen is that when you have these two water molecules reacting with each other, hitting each other with enough energy, so on and so forth, what you're going to find is that it's going to make H3O plus. All right, so this is your hydronium plus hydroxide. All right, so what we have here is that due to the fact that water will auto-ionize, all right, and this happens, H3O, it will be the acid component of water, while you have hydroxide will be your base component of water. Okay, and so we see that that water still has the ability, well, actually these are the conjugates really, that water has the ability to still where one water molecule will donate a proton, while the other water molecule will accept the proton. All right, and so that way, that's how we get the H3O plus and the OH minus. All right, the conjugate acid and the conjugate base. So it turns out, at 25 degrees Celsius, all right, and this is really, really specific when it comes to the temperature, but at 25 degrees Celsius, all right, the concentration of H3O plus and so equal, and the concentration of hydroxide is 1.00 times 10 to the negative 7 molar. All right, and so if you were to have, like I say, a bottle of pure distilled water, all right, at 25 degrees Celsius, all right, you will have a concentration of hydronium to be 1.00 times 10 to the negative 7 molar, and a concentration of hydroxide to be 1.00 times 10 to the negative 7 to be molar. All right. Now, as I said, this is at equilibrium. Okay. And so because this is at equilibrium, we could write a constant equilibrium constant for this, and we call this constant Kw, which represents the dissociation of water at equilibrium. And so if you were to write down the expression for this, now remember, this is liquid, so we don't write this. So Kw in this case is H3O plus times the concentration of the hydroxide. All right. So the concentration of hydronium times the concentration of hydroxide. And so what we find here is that if that is the case, well, if each one has the concentration of 1.000 times 10 to the negative 7, then what we could say is that Kw in this case, the concentration of hydronium is 1.00 times 10 to the negative 7. The concentration of hydroxide is also 1.00 times 10 to the negative 7. So basically we're saying 1.00 times 10 to the negative 7 times 1.00 times 10 to the negative 7. So ultimately Kw is 1.0 times 10 to the negative 14. All right. And so what we have here is that the equilibrium constant of water in this case is equal to the concentration of hydronium times the concentration of hydroxide, which is equal to 1.0 times 10 to the negative 14. So what is the implications of this? Well, the importance of this equation here, Kw, really, it all applies to all aqueous solutions, not just pure water. All right. And the reason why is that because this times this always gives a constant number, we could apply this to any solution as long as it's 25 degrees Celsius. All right. And so if you could determine the concentration of one of these versus the other, so if you could determine the concentration of hydronium versus the hydroxide, whatever the case may be, then we could actually figure out if the solution is acidic or basic. All right. And so, for example, if the concentration of hydronium is greater than the concentration of hydroxide, then the solution is acidic. All right. If the concentration of hydronium is less than the concentration of hydroxide, then the solution is basic. Okay. And so using this equation, right, we could actually figure this out. If hydronium, a portion of the solution is greater, all right, or the hydroxide solution the portion of the solution is greater, and then you could actually figure out if the solution is acidic or basic. So let's look at an example. So let's say that, all right, so we know milk, all right, milk has the hydronium concentration of 4.5 times 10 to the negative 7. All right. So now the question I will ask is, okay, well, what is the concentration of the hydroxide ion in the milk? Because milk has both, right? And all solutions have both. Now the question is, one will be more than the other. Now, once you can figure that out, then the next question I will ask, well, is this solution acidic? Is it basic? Or is it neutral? Okay. So that's the next question. All right, so let's go ahead and we can figure this out. Well, we know that Kw is equal to the concentration of hydronium times hydroxide equals, not equals 1.0 times 10 to the negative 14. Sorry. All right. And so in this case, we know what's the hydronium ion. All right, we just got to solve for the hydroxide ion. Okay, and so if that's the case, to figure this out, all right, so we're solving for the hydroxide ion. So it's 1.0 times 10 to the negative 14 divided by the hydronium ion. Okay, so then we could just kind of substitute this out, where we have 1.00 times 10 to the negative 14. All right, remember, this is our hydronium ion, so I'm going to put this here. All right, so it's 4.5 times 10 to the negative 7. You put this in your calculator, and you get 2.2 times 10 to the negative 8 molar. So this is your concentration of your hydroxide. All right, so it's 2.2 times 10 to the negative 8. So now when you're comparing this number with this number, we find that the concentration of hydronium is greater than the concentration of hydroxide, so that it makes it that this problem, or milk in this case, is actually slightly acidic. All right, because the concentration of hydronium is greater than the concentration of hydroxide, thus, like we said over here, so thus it is an acidic solution.